And today I have a physics A-level question for you, and I'll be using this question to dive into multiple concepts about principle of flotation, Archimedes principle, pressure and liquid, pressure and air, and finally I'll explain a formula that I will show you later. So let's just have an overview of what we're going to do today first. So this is a A-level physics question, and it's interesting because it makes you think about certain conceptual ideas and why the formula is the way it is. So first, let's solve this question, and I'll be providing a formula, but I'll not be explaining how it's derived first. Then so of course we want to understand the formula, and that's what makes us and that's what this video is for in the first place. So in the process of explaining the formula, I'll explain a lot of things first, then finally we'll lead up to the explanation of the formula. So first I'll talk about pressure in air and liquid. Then I'll talk about how pressure acts on solid. Usually the solid is submerged in liquid. And then I'll talk about flotation. So I'll talk about upthrust, okay, which is the rho GH formula. Sorry, it's the rho GV formula that you're all familiar with, I hope. And then finally, okay, then I'll talk about something interesting called effective volume, or effective volume, yeah, which is basically what happens when you have let's say a water that is submerged, let's say you have a cup that is submerged in the water like that. So what volume do you take? Do you take the volume of the, so you push, I'm sure we've all done this as kids, right? You take a cup and then you push it vertically down in like a swimming pool or a bowl of water, and then the water level is like that. So then this makes us ask the question, what is the volume that we consider? Do we consider the volume of the cup itself, the physical material, or do we consider the volume that is, the answer is we consider volume that is submerged, basically. And then we'll talk about this question. Okay, so what is this question in the first place? So okay, this is the overview of the video. So if you are interested in just solving the question, then you can just stop here. But of course, being in intellectual pursuit, we will try to answer the rest of the questions and explain the formula. Okay, so first of all, let's answer the question. So the metal nugget is floating between some water and mercury, and the density of the metal nugget is higher than the density of water but lower than the density of mercury. So if you put the metal nugget in mercury, it will be floating where some parts is under the mercury surface and some parts is above the mercury surface. Whereas if you put the metal nugget in water, then it will sink to the very bottom. And but what if you have somewhere in between? Then the metal nugget actually sort of rises a bit from as if it was just in mercury. So if you have the metal nugget only in mercury and the rest of it is air, then it will sink quite a lot. But if you put water on top, you actually make the metal nugget float a bit higher. Now this kind of doesn't really, it might go against your intuition, because if you think about it, right? So what I'm trying to say is that you first have the mercury, and then like the metal nugget is floating, let's say like that, okay? Then you add water on top. So you imagine the metal nugget is floating the mercury, then you add a bit of water, you pour water in. Then what happens is the metal nugget actually goes higher. So at first this doesn't seem to make sense, because if you pour something on the thing, wouldn't you be like adding more forces on the object? Well, the short answer is when you pour water, you're applying forces on the surface of the mercury as well, and these forces in a sense translate to pushing the metal nugget higher. Of course, this is very layman, and and the purpose of this video is to explain why that is so lah. But the correct intuition here is that when you put water, you're increasing the pressure at this surface, which increases the pressure at the bottom as well, which is why and although you do increase the pressure on the top surface, you're increasing the pressure on the bottom surface more because of the difference in densities. So that is the intuition. But so the question, okay, sorry, back to the question, I digress. So the question asks us to find the ratio of the volume of the nugget submerged in water to that of mercury. So we draw this imaginary line. There'll be some part which is in mercury, we call it volume A, and some part which is in water, which we call it volume B. Okay, so first of all, when this thing is floating, the vertical component of the force, so net vertical force equals to 0. So what are the vertical forces acting on this metal nugget? Number one is the upthrust, which acts upwards, right? And then number two is the weight, which acts downwards. So that's all the vertical forces there are, and that equals to 0. So now weight is simply just density of the metal nugget, rho n, I'll denote it with n for nugget, times g times a plus b. And then the upthrust equals to okay, so this is the part where I give you the formula. So for now you just absorb it. It's equals to rho mercury g a plus rho water g b. This is the formula that we seek to explain in this video. This is the magical formula that we'll explain in this video. So I mean, it sort of makes a bit of sense. Yeah, it sort of makes a bit of sense, but when you first see it, you might be wondering, wait, how is that valid? But okay, it's okay. But I'll just give you this formula for now, and let's apply into this question and see what we get. And the answer is we get the correct answer. So if we put this into the second equation, then we get so the upthrust is equals to 13600 G A plus 1000 G B minus 7900 G A plus B. So if we do this and then we evaluate it, we'll get that just subtract the common, just pull together the common terms. So 13600 minus 7900 equals to 5700A, and so we cancel the G first. Okay, sorry, I forgot to mention that. Then 1000 minus 7900 is minus 6900. B equals to 0. Then we want to find the ratio of the volume submerged in water to that of mercury. So we want to find B over A. And I believe that isn't too hard. That is just 57 over 69 equals to, punching into the calculator, we get 0.826 to 3SF. So this is 3SF. And that is in fact option B, and that is the correct answer. So if that is all you're looking for, then that is all you need to watch. So thank you and have a nice day. Leave a like, comment and subscribe if you enjoyed this video. But otherwise, for the curious people out there, let's proceed to find out why this formula for upthrust is the case it is. So okay, let's first review what pressure is. So okay, pressure in air and liquid. So we want to ask the question, in this case we want to ask the question, if I have a bunch of air, okay, I have a region of air, and I know the pressure at this point, let's say it's P0. How do I ask what is the pressure at another point, let's say, or another point, and the answer to that is the pressure at all other points is P0 also. there's a small caveat, but I'll talk about it later. So that's very simple. So this is the case for air. So for air, pressure is the same everywhere. Okay. So when people say I have a this CO2 cylinder and it has a certain pressure, they just say one number, right? That makes sense because the CO2 is only at one pressure. It's the same everywhere in the gas. Whereas for liquid, the story is a bit different. So if a liquid and let's say we know the pressure here, let's say it's P1, okay? Then we can ask the question, what is the pressure, let's say at the same water level, what's the pressure here? And what is the pressure here at a different level? So it turns out at the same level, the pressure is P1. Whereas at a different level, let's say this level, separated by a height h, the difference P2, the pressure P2 is equals to P1 plus rho GH. So this is for liquid. Rho is the this thing that looks like P is called rho, 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 and it represents the density of the liquid. So over here, okay. So so in order to find the pressure at P2, if you know P1, you need to know two things. One is the density of the liquid and one is the height. Then G is just the 9.81. Okay, so now that answers the question. Pressure is not the same everywhere, but pressure is the same for equal heights. If you are the same height, then your pressure is the same. So P1, P1. This is P2, P2. Everywhere here is on the same level as this P2 is P2. Okay, whereas there's a difference in pressure for different heights. So that is essentially all you need to know. So okay, then what happens when you are at the liquid air interface? So let's say we have a basin of water or some tub of water, and so outside here is P naught, right? So what if we have a level here, horizontal level here, and we want to find what is the pressure here, let's say P1, then and this is from the surface. Let's say we don't know the pressure anywhere in the liquid, but we do know the pressure at the surface of the liquid, at the air above the liquid. So then what is the pressure? So let's say it's height h here. Then in that case, we need to find the pressure at the surface, because the pressure at the surface, if we know the pressure right below the surface of the water, then we know the pressure, then we can find the pressure inside the water via the formula P2 equals to P1 plus rho GH, right? Because then it'll just be this pressure plus rho GH. So what is the pressure at the surface? Well, it turns out the pressure at the surface of the air-liquid interface is P naught. So the pressure at the surface is P naught. So in the end, P1 is just equals to P naught plus rho GH. And that makes sense, right? Yeah. So if we graph what it looks like, so if we have, let's say we have okay, so let's say we have a column of water and some liquid here. So this is, outside here is air, and inside here is liquid. Then if you graph the pressure with respect to the volume, so this is position, or this is the height, and this is the pressure. If we graph it, what it's going to look like? It's going to look like this at first. Remember I said pressure is the same everywhere in air. So it's going to be P naught, and then it's going to increase. As you go lower, pressure increases. If you are a diver or you have ever been to the bottom of the swimming pool, you can feel it from the pain in your ears. So as you go deeper, you feel like your ears feel like there's something pushing on it. It's an uncomfortable feeling, but yeah. So if you go lower, the pressure increases, which is why divers, they can only go to a certain depth before they die due to the high pressure, because remember it's rho GH, okay, and yeah, it's rho GH, so the density of water is not small. So the lower you go, the more pressure you experience. So this is what the pressure height graph looks like. Well, okay, so let's talk about air again. So previously I said pressure is the same everywhere, right? That is not 100% true. Air is actually, we talk about over here, we talk about air and liquid, but actually this applies to fluids. This principle of this liquid thing, this liquid formula here, P2 equals to P1 plus rho GH, it applies to fluids. So actually instead of liquids, I should say fluids. So instead of liquids, let's replace it with the word fluid. As actually air is a fluid. So fluids are liquids and gases. So actually the formula here applies for air as well. Well, then why did I say pressure is same everywhere? That is because the density of air is really low. So if I have, let's say I have it's funny to say this, but let's say I have a container of air, okay? So I have a container of air, and I want to ask what's the difference in pressure here and here. So if this is P1, this is P2, so of course P2 minus P1 equals to rho of air GH, right? Where H is the vertical distance that they are separated by. But rho of air is very small. So if H is in the context of, let's say if H is approximately let's say 100 meters or like 1 meter or something, in the context of a room, let's say in the scale of a room where the air we're breathing in right now, the H is really small, and hence this term is approximately 0. So P1 approximately equals to P2 because rho of air is very, very small. It's not approximately, yeah, it's very, very small. So rho of air is very, very small. However, you might have heard that when mountain climbers, they climb up Mount Everest, right? Then the air pressure drops. So they need like some sort of CO2, no, they need some sort of O2 tank, right? Some oxygen tank and things like that to help them breathe. That is because when you climb Mount Everest, the H here is huge. And even though the density of air is low, because the height is on the scale of kilometers, the pressure difference is actually significant. So if you have the Earth's surface here, then actually the higher you go, the lower the pressure gets. Eventually you reach the depth of space where there's no more air. So yeah. So actually my statement that pressure is the same everywhere for air is not entirely true, because if you go to very high heights, right, like Mount Everest, then the pressure is not the same as what happens if you stay on the ground. So the difference in air pressure from the top of Mount Everest to and the bottom of Mount Everest is not the same. There's a difference in pressure, but that's because of the huge differences in height that is in that scenario. Whereas for the case of most of the cases in like when you pour water in a coffee mug, the air in your room that you breathe, the height is very small, so the pressure is almost the same everywhere. Okay, so actually this formula P2 equals to P1 plus rho GH, this is the mother of all formulas, because this is the rule for air and water. But just remember that for air, because the density rho is small, the P1 is approximately equal to P2. So yeah. So that is so now we know, in summary, P2 minus P1 equals to rho GH. And that is the key takeaway. So okay, now we know how to calculate pressures. Okay, so now we're done with 1, we're done with 2. So let's talk about how pressure acts on a solid. Okay, so when you have a, let's say you have a, let's say I'm in some body of water. Okay, so so I put a solid object inside. So let's say I know the pressure at this point. And let's say it's P. Then this pressure would cause when you put a solid object inside a liquid, this pressure would act on the solid. But how would it act? Well, the answer is it will act in a normal direction. So normal direction means perpendicular. So I draw a bigger object here. So let's say I know the pressure here. Then the force that the liquid exerts on the solid is then normal to the surface. So there's a dA, the normal vector, for a small area, and the force, which is a vector, equals to P, which is a scalar, times dA, which is a vector. So in this case, your area is an area vector. So this equation makes sense because you have a vector on the left hand side, you have a scalar, and then you have a vector. So scalar times vector is a vector. So what I'm trying to say is that this pressure is isotropic. Meaning that it doesn't have a preference for a certain direction. In a sense, the pressure acts in all directions. But yeah. So if I don't put a solid object inside, right? You can imagine that the pressure acts in all directions. So like if I have this point, the pressure sort of acts in all directions. But if I do put a solid object, then the force exerted by the fluid, by the liquid, on the solid object is then given by, the direction of the force is then given by the normal vector, and the force is given by P times area. So pressure equals the force divided by area. Yeah, force equals the pressure times area. So that's how the pressure of air or a liquid acts on a solid body. Okay, so now we know how pressure acts on solids. So that we can finally answer the question of how upthrust originates. So if we have some body of water, okay, and let's say we have some so in order to explain upthrust, I'll split it into two. I'll first do the case for a cylinder because it's easier, and then I'll do a general shape. So in the end, both formulas are going to be rho GV. So it shouldn't, in the end, it doesn't matter. But I'll do the cylinder first to illustrate an example. So the pressure acting on, so upthrust is the vertical component of the force. So we can, for the pressures, for the forces acting on the walls, they cancel out horizontally. So we just need to worry about the vertical components. So there's two surfaces here, 1 and 2. So let's say the pressure at the first part is P1 and the pressure at the second part is P2. Remember that this surface lies horizontal to the surface of the water. Basically, this surface of the cylinder is horizontal. So pressure everywhere is P1. Everywhere on the surface is P1, and the pressure everywhere here is P2. But because there's a difference in pressures P1 and P2, so P2 minus P1 equals to rho G H, where H is the height of the cylinder. Because there's a difference in pressures, Okay, so then what is the net force acting on it? So let's say this surface on the top and bottom, they have cross-sectional area A. So, so the force, so upthrust equals to the force. So remember what I said about how pressure acts on a solid body, right? So on the bottom, the pressure would exert a force on the body upwards, whereas on the top, the pressure would exert a force on the body downwards. So just draw this line for convenience. So at the top, the pressure will push it down. At the bottom, the pressure will push it up, because at the top, the liquid is above the solid, whereas at the bottom, the liquid is below the solid. So upthrust equals to F2 minus F1, because F2 is upwards, F1 is downwards. And this equals to P2A minus P1A. And this equals to rho GHA. Well, what is HA? HA is actually just the volume, because we are taking the height times the area. So it's actually just rho GV. And that is, you can see that the case of a cylinder is very simple to derive the upthrust. Well, this can be generalized. Well, actually, we don't need it to be a cylinder. It can be just any, it can be any shape, as long as the upper and lower surface is the same. Okay, it's not very the same here, but yeah, you get the idea. So it can be like a triangle, and this derivation will still work and stuff. So okay, so okay, so now for a more general shape, this one is going to be a bit challenging, but it's fine. So if you have a more general shape, let's say something like that, okay, the upshot of it, this might not be a completely convincing argument, but upshot of it is that you can split this general shape into many small cylinders, and in the end is going to be rho GV also. So let me try to convince you. Okay, that's a so of course, because the upper surface is not exactly horizontal, upper surface is like that, right? So the force will be acting in this direction, and the corresponding bottom surface will be something like that, and the force will be acting in this direction, right? But when you end up taking the vertical component of this, when I'm taking the vertical component, remember we don't care about horizontal components for now. The horizontal components would balance out, but it would cause a the horizontal components would balance out, but it will cause it might cause a torque on the body. So that's why sometimes when you throw an object in the water, it rotates. But the upshot of it is that when you consider the vertical component, each one of this is like a small area dA, and then each one of it has a difference in height h. And when you integrate over the surface of the entire solid body, so integral of rho dh, hda, sorry, is equals to v. So essentially, the difference in f2 minus f1 equals to integral of rho g h dA, and that equals to rho gv. So I know this is not an entirely convincing argument, but yeah, if you work through, sorry, I don't want to go through the exact derivation because it involves quite a lot of complicated cosines and sines and resolution of vectors, but this is the argument that if any solid body of any shape, in the end, the integral over here is just going to give you the volume of the object. So I apologize for the lack of rigor in this argument, but I hope that the cylinder case is convincing enough to tell you why is rho GV. I mean, the cylinder one is completely rigorous, but in this case, because I have to do some integral and I have to resolve the vectors vertically and horizontally to show that they cancel out eventually. I will just provide this argument in order not for the video to get too long, but I can make a video on the resolution of these vectors and the integral another time. If you want it, leave a comment in the description below. Oops, and I appear to have run out of pages. Let me just okay, so let me just open another document. Okay, so let's go back here. So okay, so we have covered how the pressure acts on a solid, and we have covered what the origin of upthrust. The origin of upthrust is the difference in pressure when you have a difference in height. So the root cause of upthrust is when you have a difference in height, that when your object is submerged, right, there's pressure that exerts a force on the bottom surface and the top surface of the object. And because the pressure is different, that causes a net force on the object, and that is upthrust. And the upthrust we have seen is equals to rho GV. Okay, so let's talk about the cup question. Let's say we have a bucket of water, and then we have some cup that we inverted and pushed down. Let's try to derive the upthrust in this scenario. Okay, for simpler purposes, I'll draw a cylinder cup. Okay, so this is the alright, so first of all, there's pressure P naught acting on the cup above, on this upper surface, and then for the bottom surface, let's say this submerged region is H. Okay, so on the bottom surface, the pressure exerting on the air, so remember that this is air, this is liquid, and this yellow part is a solid. So the pressure on the bottom part over here, between the air and liquid interface, the pressure is equals to P0 plus rho GH. So in the end, if you have the same area, so the pressure acting on number one, the solid pieces here, the solid liquid interface here, and number two, the air here. That means that the pressure of the air inside here is also P1, because the pressure on the liquid air interface here, between the air and the cup and the liquid below this air, at this surface, the pressure is P1. That means the pressure of the air inside is also P1. And because the pressure inside air is the same everywhere, the pressure here is also P1, right beneath the surface here. So in the end, what are the forces acting on the cup? The forces acting on the cup is number one, this P naught over here at the top of the cup, and number two is this P1 here on the bottom surface of the cup, and number three is these parts over here, which is also P1. So there's P1 here, then there's P1 here, and there's P0 at the surface. So what do you get in the end? You get that the upthrust, remember the upthrust is the forces acting on the cup itself, not the air inside the cup, but the cup. But it's due to the fact that the pressure inside the air is the same everywhere, that you can just take P1 at the surface here, the green surface. So this is equals to P1 times, let's say this is a small area, let's just call it A1 plus P1, and let's call this surface A2 plus P0, and and this total area is equals to A1 plus A2. Oh, sorry, it's not a plus. This is a minus because it's acting downwards. So in the end, you get P1 minus P2, A1 plus A2. And this is just equals to, so A is essentially the total cross-sectional area of the cup. So this is total cross-sectional area of the base of cup, and this is P1 minus P2 is equals to P1, wait, sorry, why am I, it's not P2, it's P0, P0, yeah, P0. P1 minus P0 based on this equation is equals to rho g h. And what is h times this total cross-sectional area of the base of the cup? Well, that is just the submerged volume, because if we take let's say we take the blue color over here, okay, that one can't be seen. Let's say we take this orange color here, and we take, so what I'm trying to say is that h is this height here, right? H is this height, and A is this cross-sectional area. So essentially I'm taking the entire volume here, taking this entire volume of the, so this is essentially equals to volume of cup including air inside the cup, including the air inside the cup submerged. So this is essentially the effective volume. So what I'm trying to say over here is that if we just naively apply the rho GV formula, then we might think, hey, there's very little bit of the cup that is submerged, so the upthrust must be pretty small. But according to this derivation, where we put the cup inside, the upthrust is actually including the volume of the air that is submerged underneath as well. Now this is fascinating because this is interesting because if you fill a cup with water and you push it down like that, then the cup will just drop, would probably just sink, because the density of the cup material itself is higher than the density of the water. So it'll sink. But if you invert the cup like that and you push air inside, because the air is much less dense than the water, but you're still displacing volume, so you're still causing upthrust. So in the end, the upthrust is going to be bigger than the weight of the cup, because the weight of the cup is mostly contributed by the material of the cup. It's not contributed that much by the air. So this is essentially effective volume, and that is why you can have a huge metal ship where the density of metal is definitely higher than water. But if the ship has a lot of air inside, you can use this to essentially have an effective density of the ship. But so it's sort of a because you're making use of this effective volume of the air, so you're actually causing the upthrust to be higher than the weight. So this is an interesting principle because it really tests your understanding of how upthrust originates from. If you just blindly apply rho GV thinking that V is the volume of the material of the cup, then you're going to get the wrong answer. But V is actually the volume of the cup, including the air that is submerged. So that is what I meant to say by effective volume. So I hope this example gets you thinking a little bit more about upthrust and how to apply the principle of flotation in certain cases where the formula is not just a result of blind application of rho GV. And now this brings us to a final example, which is the question in the first place. And that is also another instance of a question that you cannot simply apply blindly rho GV, because you must understand, if you want to apply the correct formula, you want to understand the correct formula, you must understand the principles that go behind the formula. And that is the whole purpose of this video, to illustrate how you can go from first principles of the difference in pressure. I can go from those principles to the derivation of the correct formula. Okay, so now for the final question, we have Mercury. I shall denote Mercury with this gold color. And then you have water. Okay, in this case I'll use a cylinder, but that's just for easier derivation. It actually really it applies to any general shaped object as well, similar to the argument I made previously about the integral of HdA. Yeah. So okay, so first of all, what are the surfaces that have the forces acting on them? So there's this surface, okay, and then there's this surface. Alright, so if the so the upthrust equals to F2 minus F1. Now what is the F2 caused by? It's caused by pressure P2 at the surface. And what is F1 caused by? It's caused by pressure P1 at the surface acting downwards. Or rather, P1 at the surface, isotropic pressure, but it causes the force to act downwards. So, so what is P2 minus P1? So F2 minus F1 is just A times P2 minus P1, where A is the cross-sectional area of this cylinder. So P2 minus P1, in this case, is not as simple as rho GH, but it's actually because the density of the liquid changed halfway. What I can do is I can insert a certain pressure. I can insert this P3 at this surface. So I'm just going to say P3 is pressure at this surface. P2 minus P3 plus P3 minus P1. So I've inserted this is essentially 0, right? But I've inserted it in between because P2 minus P3 now is all in Mercury. The difference in height here, I'll call this H, I'll call this H1, and I'll call this H1. So this in this case is a rho Mercury G H1, am I right? Plus, and what is this thing? P3 minus P1 is, we call this H2, is just rho water G H2. So I've inserted this P3 because it's the boundary between the surface between Mercury and the water. It's the interface. Interface is the right word. It's the interface between Mercury and water, and P3 is a common. It's a pressure. It's at this interface, and it's equals to the pressure a bit above the interface in the water region, and also equals to the pressure a bit below the interface in the Mercury region. So P3 acts as a bridge between the Mercury and the water. And what do we see? Oh, we see that this is rho mercury G H1A plus rho water G H2A. And H1A, remember what is A? A is the cross-sectional area. H1 is the height sum between the interface and the bottom surface. This H1A is actually just the volume of the cylinder inside the mercury. So this is just G V mercury. It's just the volume inside the mercury plus rho water G. H2A is just the volume of the cylinder that is submerged inside water. And that is our answer. So upthrust of a object that is submerged both in two liquids, in mercury and water, is simply the sum of their densities times the G times the volume in which the liquid they are submerged in. So I know this final answer seems a bit short. It's kind of anticlimactic because we went through all the trouble of this and the principle of flotation and stuff like that. But I hope that you see why this entire video comes together, because we have gone through the foundational principles, the foundational concepts of origin of upthrust and transmission of pressure across interfaces of fluids. So it is a few key ideas that is important for this video. So I'll just do a summary. So first, we did the question. Then I talked about pressure in fluids. I wouldn't say air and liquid now, I'll just say fluids, because fluids consist of air and liquids, encapsulates both. And this is governed by the formula difference in pressure equals to rho times G times the difference in height. Then I talked about pressure acting on solids, which is essentially F equals to P dA, where the direction of F is given by the normal vector. And then I derived upthrust equals to rho GV for simple cases. Okay, for like the cylinder and a general shaped body. However, upthrust equals to rho GV effective for inverted cup scenario. And lastly, upthrust equals to rho mercury G V mercury plus rho water G V water for two liquids. So this is summary, but the upshot of this is that whenever you see a question where it's a non-standard, where this kind of formula doesn't immediately apply, you can always fall back to these first two principles. And these first two principles will help you derive the correct formula, such as in 3, 4, 5. So in the end, what I want you to take away from this video is that upthrust is rho GV. You can apply the upthrust formula for simple questions, but as long as you understand 1 and 2, if you understand 1 and 2, then 3, 4 and 5 should be natural. Because so if you in the future, if you see any other questions like 6, 7, 8, where there's more cases of upthrust, you can always look back at 1 and 2, at points 1 and 2, because these are the foundational governing principles of pressure in fluids and pressure in physics. So this is what understanding physics is about. It's about understanding the principles and how you can derive the different results from it. It's not just about memorizing formulas. you must understand the principles behind them, and hence you can make further extrapolation and understand more complex scenarios. So I hope that this was a very good question, because it got me thinking about pressure, about the first two principles, and how, and that's why I decided to make a video on it. So I know it's a lengthy video, but yeah, thanks for sticking with me all the way. And if you enjoyed this video, leave a like, and if you didn't enjoy it, just leave a dislike or give me some feedback in the comments. So anyway, I hope that you can take this philosophy and apply it to other areas of physics, and do send me any interesting questions if you are stuck. So yeah, that's all for today. Bye.